Alright, hello. So, for kinetics, energetics, you remember we covered previously, energetics got three different types of experiments, right? For kinetics, it's relatively simpler. There's only two different types of experiments. Number one, we call it the clock method, or also known as the initial rates method. But I just prefer to use the term clock method. Okay. Uh, Usually, realistically, the only two types of clocks experiments they can give you is number one is sulfur clock, where you wait for the white PPT to form. The other one is iodine clock. So, even if you haven't done both of them in practical, you should have been exposed to both of them at least in planning already. So you should be familiar with what the color change is. Basically, if you don't already know, right, sulfur clock, the endpoint of a clock experiment is always some kind of color change. So it's very cool one. You just sit and wait, hands on the stopwatch, you wait for the conical flash to change color, then the moment you see a color change, you stop the thing immediately. So for sulfur, there will be a white PPT, and usually this is the one you may recall we use a card marked with an X, and we place the conical flask over this particular card, and then the moment the white PPT forms such that the X can no longer be seen, stop the stopwatch immediately. That's the sulfur clock. Iodine clock is even cooler. You add starch indicator, and then after that, you wait until the solution turns from colorless until when there's enough iodine being formed, that's the end point of the reaction. Because of the starch indicator that's present, everything is colorless, but the moment you get enough iodine form, it will turn the starch indicator to blue-black. This one, the color change is even cooler. I have unfortunately never ever seen it in real life because I've never done it in real life. But hopefully tomorrow, 25th of August, is in the prelim practical exam. Hopefully, I'm hoping this experiment comes out tomorrow because I always wanted to try it actually. It's a really cool experiment. Yeah, I've done the sulfur clock before though, in practical. This one I haven't done before. So we'll see what happens tomorrow. Anyway, basically, clock method, the idea is that you have multiple different volumes. So a bit like for continuous variation, you need to draw a table. Now I'm revising what the table looks like. I'm not entirely sure. I need to remember what it looks like, so bear with me as I remember and retrieve my memory a bit. So basically, same as continuous variation, the idea is to keep the total volume constant. But unlike in continuous variation, you can top up with deionized water. So usual practice, right? Always have a column that says total volume. Let me move that a bit. Yeah, always have a column that says total volume. Even though the total volume is constant, you might think that it's redundant. You should always have a column that says total volume slash cm cube. Okay, and then basically the rest of the table should look something like this. So this is what the table should look like. The total volume should be constant. Uh, Even in planning, usually I think even a planning question will specify the total volume. It will either be 25 cm cube or 50 cm cube. So you don't need to worry about that. But you vary the volume of Fa1, which is the reactant, and then you top up to make sure that the total volume is constant using deionized water. And then after that, you record with the stopwatch the time taken for the distinct visual change, whatever the distinct visual change happens to be. So yeah, as I said, uh, the distinct visual change for the iodine clock is really cool, and I want to see it in real life one day. And then this is all of your data that you collect, right? Got one more column here for the derived data. Now, even though this isn't a physics paper and chemistry isn't as 讲究 as physics and bio are when it comes to small things like that, okay, maybe calling it small things isn't a very good idea. It's actually quite a big thing. As much as chem isn't that 讲究, please remember that by right, strictly by right, derived data cannot be more SF than the data that you collect. So what is the precision of the stopwatch, people? The precision of the stopwatch, by right, according to human reaction time, is 0.1 seconds. But by left, almost always, they will ask you to record to the nearest second. But when you are doing a planning experiment, can you ask the experimenter to record to 0.1 seconds? Can, but human reaction time, so you need to keep that in mind. Usually, best practice is really just to record to nearest second. I don't think you will ever get a clock experiment that's so fast you need to record to greater precision than that. So therefore, the 1 over t is also going to be to the nearest second. So if your seconds got 2 SF, like let's say 1 0 seconds, 1 2 seconds, then your 1 over t, you cannot give, so 1 over t is 0.1 something, 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 something. No, if your t, this column is 2 SF, this one by right should also be 2 SF. Okay, I don't recall them penalizing you in a chem paper or things like this. If it was a physics paper, they would be very, very 讲究 and dot marks off your table. But I have no idea, and in the absence of better information, it's better to just be safe. Okay? So, after that, you are going to plot a graph of 1 over t against VFA1. Now, FA1, I'm sorry if I didn't mention this, is the reactant being investigated. So you are going to plot a graph. Okay, now there are two different things that this graph could look like. So I'm going to move this over and duplicate this. This will also test a bit of your theory, okay? Can you recall for me, if my reaction is first order with respect to the concentration of Fa1, what does this graph look like? So what is 1 over t? Why do I need to add this additional column 1 over t? Because 1 over t ultimately is a measure of rates. And then because the total volume is constant, what is this VFA1 measuring? Essentially, it's measuring concentration in a way, right? Because you keep the total volume the same, but you vary the volume of the reactant being investigated in the mixture. This is essentially a rate concentration graph. So, to revise your probably very, very rusty theory, for a rate concentration graph, if the reaction is first order with respect to Fa1, the reagent being investigated, its rate is going to be directly proportional to the concentration of Fa1. That is, after all, the definition of a first order reaction. For the rate of reaction to be in first order with respect to the concentration of a particular reactant, it means that when the concentration of that reactant double, the rate of reaction will also double. That's why it's directly proportional and must pass through the origin. If it is second order, if the rate of reaction is second order with respect to concentration of Fa1, then it's just going to be a quadratic graph. It's just y equals to x squared. Ta-da! Simple. Understand? So, because of this, based on the shape of the graph, we can deduce the order of reaction with respect to the concentration of Fa1. Okay, there are more things I want to nag about kinetics later, but having introduced you the clock method, I'm going to introduce the arguably more fun and more high cortisol sampling method. Technically, okay, technically, there are two different ways you can do the sampling method. One is sampling followed by titration. One is sampling followed by gas collection. If you take bio, you know that gas collection, how to draw the setup for gas collection. So hopefully bio will have provided pretty good training for how to draw the gas collection setup. The gas collection setup, by the way, using a graduated gas syringe is found in the chapter 3 notes, the gaseous state lecture notes. Okay? But the thing is, I have never done or seen any question anywhere in chem that asks you to perform gas collection or plan for gas collection. So if you really so unlucky that you kena gas collection in planning, then good luck to you lah. Hopefully you'll remember how to draw properly. And when you do, you'll be very grateful to your bio teachers. Anyway, sampling method usually is sampling followed by titration. So I'm going to talk about sampling followed by titration. 两个很重要的点 ，OK, for sampling followed by titration. 第一点就是 you have these various time points, right? Can you make sure, please, okay, that you pipette or withdraw the liquid? Usually, we will use a 10 cm cube pipette, but sometimes they can ask you to use other things like the dropping pipette lah, whatever kind of apparatus you use to withdraw an liquid of the reaction mixture. please plan. Okay, I'm talking with respect to planning now because ultimately, as I also said in the energetics video, if you are given instructions to follow, that's all well and good. If you need to write your own instructions in planning, that's when things get scary. Okay, so can you please make sure when you are doing planning and also when you're doing your practical, in case you sotong and never read the instructions, please do a sanity check. Make sure that when you're doing a sampling experiment, you need to withdraw an aliquot before the planned time point. And then you quench with whatever thing is in large excess at the time point. And then titrate immediately. And please remember that you only can perform each titration one time. So if you overshoot the endpoint, then GG lah. You're dead if you overshoot the endpoint. That's why this is the most difficult, in terms of manipulative skills, most difficult experiment in H2 camp. But it's also damn fun. I love it. Anyway, let's say I want to investigate the order of reaction with respect to concentration of Fa1, and I want to use the sampling method. What I will do is the reaction is going to be something like this, right? Fa1 plus another reactant is going to give you a product. Okay, this other reactant R is going to be in very large excess. And if you remember your kinetics theory, if something is in large excess in a investigation, we say that it's pseudo zero order. Okay, so therefore, because this is in large excess, essentially, even though the rate equation may be something like this, I have no idea what this power is yet. I'm trying to find this power. Even though the rate equation might have been like this. If this thing is in large excess, such that this thing is almost constant, this is a constant, this thing is also a constant. So essentially, I'm isolating this so-called, so that I can solve for n mathematically. You get the vision? Fantastic. So basically, I'm going to let this reaction proceed for a bit, and then I'm going to take some aliquots from the reaction mixture. Then I'm going to titrate it with something else. Let's call this something else Fa3. So let's say Fa1 plus I titrate with Fa3. So this thing goes in the burette, okay? And I will form something. I don't know what that something is. Basically, right, I will then plot a graph of volume of Fa3. No, I'm so sorry. Wait. Oh, yes, it is volume of Fa3 against time. So this one, remember for my clock method, I start and stop the stopwatch multiple times for each row of the table. And remember, in planning, how many rows must there be here? At least 5个, okay? So this one, I start and stop the stopwatch multiple times. This one, I start the stopwatch once. And from the time I start the stopwatch to the time I stop the stopwatch, everything is very, very, very high cortisol. Okay, your graph will look something like this. Oh dear, no. It's supposed to be asymptotic. I will blame the fact that I'm writing on a glass screen for the fact that that graph was terrible. Anyway, can you recall for me, what is this thing a proxy for? Do you notice that volume of Fa3 needed for titration, right, is simply a proxy for the concentration of Fa1, which is the concentration of a reactant remaining in the reaction mixture. Do you understand why that is the case? So as a result, right, hopefully this will be familiar from theory. Do you remember how to label your graphs like this to find half-life? Your concentration time graph for reactants. Something like this, right? So this is going to be half of the initial, 1/4 of the initial. If n is equals to 1 and it is first order, even though I know my drawing is not very good here, if it's first order, it means that the first t half is equals to the second t half. The half-lives are constant. If it is second order, these two half-lives will be increasing. Okay, that's basically the idea. So we assume that these two half-lives are constant. Once again, okay, half-life is constant. It means the reaction is first order with respect to concentration of Fa1. If T half is increasing, it means the reaction is second order with respect to concentration of Fa1. Clear? Or rather, the rate of reaction is second order with respect to concentration of Fa1. Now, if it's first order, can you please recall first order? There's an equation that we can use if it's overall first order, which is the following. So if you can read the half-life T half off from the graph, I'm so sorry, it means that you can use this equation to solve for K, the rate constant. Understand? Okay, now for the things I want to nag about kinetics experiments. As I have already nagged about, no matter whether for sampling method or for clock method, there will always be one reagent that is in excess such that the reaction is pseudo zero order with respect to that. Second, this is not just about for kinetics, okay? It's for planning in general. Every time you write a planning step, your planning step should look something like this. Using a what apparatus? Do what? What quantity of what reagent or what reactant into what is it that you are doing? When you write what apparatus, right? This one, I cannot just say use a measuring cylinder. I use a 10 cm cube measuring cylinder, 20 cm cube, 50 cm cube, 100 cm cube, blah, 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 blah. Okay? So I cannot just say use a measuring cylinder. I must specify what's the volume of the measuring cylinder. I need to specify what is the volume of the thing I'm transferring it to. Okay? And then when I give the quantity, okay, this quantity has to be appropriate to the precision of whatever apparatus I'm using. So for example, if I have a 10 cm cube measuring cylinder, you go back to your memories. Do you remember what a 10 cm cube measuring cylinder looks like? What's the smallest division on the 10 cm cube measuring cylinder? It's 0.1 cm cube, right? And then remember, we can read any apparatus. We can read any apparatus in the chemistry lab to half the smallest division. So what is half the smallest division? Is 0.05 cm cube. So if I use a 10 cm cube measuring cylinder, I don't say using a 10 cm cube measuring cylinder, measure 5 cm cube of Fa1. I will say measure 5.00 cm cube of Fa1. Okay, as I said, this is chemistry, it's not physics. They may not be so 讲究, but it's better to be correct than to be wrong. Okay, can? Yeah, I think that's it. That's all I have to nag about for kinetics and for practical in general. Hopefully, things will go well tomorrow. And yeah, I think that's all. Bye bye.